Hello everyone, welcome to my channel EC on Tips. I am Samiksha Shrivastava. In today's lecture, I will be teaching MOS operation. So MOS operation is mainly operated in four regions, that is flatband region where we apply zero gate voltage across the gate terminal, and the next one is the accumulation region where we apply negative voltage across the gate terminal, and the third one is the depletion region where we apply the positive voltage across the gate terminal, but here we apply small positive voltage. Okay, and the next one is the inversion region where we apply the gate voltage which is greater than the threshold voltage, that is greater value we apply here. And all these four regions are assumed to be operated at when the body or the substrate voltage is considered to be zero or it is grounded. So this is the criteria under which these four regions operates. So first we will study about the flatband region. So what we observe in the flatband region? So in flatband region, MOS consists of a metal, that is M for metal, O for oxide and S for substrate, that is semiconductor. Okay, so here it is MOS, that is metal, oxide and semiconductor. So in flatband region what we do is we apply zero gate voltage. If we apply zero voltage at gate terminal, we will not observe any of the phenomena here. Okay, as it is grounded and this is also applied zero, so there will be no observation. So its energy band, if we consider its energy band diagram, we will observe that there will be no change in our energy band diagram. Metal, that is the amount of energy required to remove the electron from the metal surface, that is the energy band diagram of the metal, and so goes with the oxide. Here oxide we are considering SiO2. Okay, so that will act as an insulator. And here the third one is a semiconductor, where the semiconductor is simply plotted like this, that is it consists of a conduction band. This is the intrinsic Fermi level. This is the semiconductor or the substrate Fermi level. Here we are taking substrate of p type, hence it is p type Fermi level, and this next one is the valence band level, energy level. Okay, so this is all from the flatband region. Here we observe nothing. Then the second one is the accumulation region. In accumulation region what we do is we apply negative voltage across the gate terminal. As we are applying VG, this is gate terminal, so here we are applying the negative voltage across it. So if it is negative, then here the whole negative region will be accumulated, and due to this negative charges, what will happen, here it is a p-type substrate. So if it is a p-type substrate, here will be a large quantity of holes. Okay, simply if we talk about p-type substrate, the majority will be holes and minority will be electrons. Okay, so holes and electrons. So as it is a p-type substrate, so majority will be holes. So due to this negative charge, the holes will come near to the interface of the substrate and oxide, and all of the holes will accumulate in this particular region like this. Why they are accumulating over here? Due to this negative charge. Okay, but these holes are not capable and they cannot cross this oxide layer and move to the metal surface. Why is it so? Because this oxide is the silicon dioxide. And what is the property of the silicon dioxide? It will act as an insulator. Okay, if it is acting like an insulator, so it will not allow these holes to cross to over it and move to the metal surface. Okay, so this is all in accumulation region. Here what is it? That holes are attracted to the semiconductor oxide interface. Here holes are attracted to the oxide and substrate interface. Okay, and what you will observe here is there will be an electric field that is directed towards the gate terminal. Here what will you observe? You will observe that electric field will be observed from substrate to the metal region. Okay, so this electric field is called as EOX. EOX. So this electric field is directed towards the gate terminal. Why? Because this electric field is always from positive to negative. Because this is positive, hole is a positive charge. So hence from positive to negative, the electric field direction will be in the upward direction. Is it clear? Now if you will consider its energy band diagram, then its energy band diagram, metal will be as same as in the flatband region, because metal is not affected here. Okay, and the next thing is the oxide. Oxide, you will observe here is that there is a slope observed, and similarly with the semiconductor region as well. But in semiconductors, some part is sloped and the other part is flat. Why is it so? Because these holes are accumulated in this particular region only. So they are accumulated in this particular region only. They are not accumulated the whole area. Okay. So this is observed in that particular region only. Hence, for that particular region where the electric field is non-zero, it is observed there. Okay. And in this region, electric field is 0. So here you will observe that oxide is tilted and the electric field in particular region will be tilted. Why is it so? You can learn it or memorize it by this particular trick, that is electric field हमेशा सर उठा के जीती है, which means that as you know that electric field direction is from substrate to metal. So substrate to metal, the electric field direction will be in this way. Okay, in this direction, this is electric field EOX. Okay, so due to this electric field हमेशा सर उठा के जाएगी, तो इसका हम स्लोप ऐसे याद रखेंगे that it will be in the upward direction. Okay, and in similarly here also electric field is in this direction. In this particular region, here only electric field is present. So electric field will be like in this direction. So hence it will be sar utha ke jayegi. If electric field is standing here, it will be in the upward direction. Is it clear? So upward bending of energy band you will observe in this particular region, and this is all in the accumulation region. Then the next region comes is the depletion region. In depletion region, what is it? Is we apply VG, that is at the gate terminal we apply the small positive voltage. Okay, here if we apply that small positive voltage like this, VG is a small positive voltage, so all the positive charge will accumulate over here. So now what will happen? Now first we will understand what is depletion region. So depletion region is a region where the majority charge carriers are relatively absent, where the majority charge carriers are relatively absent, which means that in p-type substrate, if we consider a p-type substrate, here the majority charge carriers are holes. What are majority charge carriers here? Holes. Okay, so holes will be absent in particular region. That region will be called as a depletion region. Is it clear? So due to this particular positive charge, how holes are represented? You all know that holes are represented like this. This is holes. Okay. So simply what will happen when this positive charge is applied across the gate terminal, then the holes will leave behind and the electron, the charge acceptor ion will move towards this region. Here the acceptor ion will move toward this and hole will be remain behind. Here hole will be in this direction and the acceptor ion will move this. Hole will be in this direction, acceptor ion this, and they all will move in this direction. So you will observe the whole negative charge deposited over here. So here what you will observe that here the majority charge are p-type. That is, holes are the majority charge, but what you will observe that the acceptor ions will accumulate over here. The negative charge will accumulate over here. Okay, electrons will accumulate over here. That is, the majority charge, that is the holes, are absent in this particular region. Majority charge are absent in this particular region. So this region is called as a depletion region, where the majority charge carriers are absent. Now the next thing, if we go to its mechanism, this explanation I have written in these lines, that is, holes will leave the negative charge fixed acceptor ions. These holes will leave that ions. Thus a depletion region is created near the surface. Near the surface you will observe this depletion region. Now if we'll study about its energy band diagram, so its energy band diagram will look like something like this, in which metal is simply like this, and then as I've told you, in this electric field will be in the which direction? Electric field will be in downward direction. Okay, in this electric field EOX will be in the downward direction, which means that from metal to substrate means electric field direction is in this direction. Electric field is in this direction. Here electric field will be observed and here electric field will be 0. Why is it here 0? Because of its straight area, because here the electric field is not observed. In this particular region electric field is not observed. Only in the depletion region you will observe this electric field. So here if you observe that this oxide layer electric field is always sir utha ke jeeti hai, hence it will be in this upward direction. Slope will be in this upward direction. If electric field direction is in this way, so you can remember that slope will be definitely in this direction. This is the best way to remember this energy band diagram. It is always asked in the university exams to draw this energy band diagram and explain these all 4 regions. Okay, so this region, this particular depletion region is clear to you all. So the next we will move to the last region, which is a inversion region. What happens in inversion region is that we apply the positive gate voltage at the gate terminal, but that is how much large? That VG should be larger, but that should be greater than the threshold voltage. Okay, so that should be greater than the threshold voltage, and if VG is positive, we have applied the large value of that. So all this will accumulate. This is VG, all positive charge, and a high concentration of positive charge will accumulate in this particular region. Okay, so there will be large positive charge accumulated in this particular region because we have applied a large value of VG, higher value of VG. So what is inversion region? If you talk about inversion region, first we will study what is its inversion means. Inversion means complete ulta. Okay, complete opposite. So if you are considering P type, so that is its opposite is N type. So this is only we will observe in this in particular inversion region. So now what you will observe in this particular diagram is, this is MOS metal oxide semiconductor. So as it is positive charge, so here what you will observe that there will be an accumulation of hole. This is what this is hole and the charge, hole, charge, hole, charge. Everywhere it is present like this. Okay, so here also what you will observe that all the charge acceptor ion will move this and it will move this in this direction. Same observation as in the depletion region, but as we have increased the concentration of this gate voltage, so here the negative ion acceptor ions concentration will also increase. They will be very much quantity. They will be in very much quantity as we have increased the value of Vg. It is negative. Okay. So this particular region will be so much negative, it will be so much content of a negative charge that this particular region will be inverted and it will behave like an n-type region. Okay, so as it is a p-type substrate, but due to this negativity or so much amount of inversion in its behavior, it will behave like a n-type material because of its negativity. Because of its high positive attraction, more negative charge will attract over here and more accumulation of this region will be there, and hence this will completely behave like an n-type material. Is it clear? So here what you will observe, that n-type region is created near the interface. This n-type region is created near the interface by the positive gate bias. By the positive gate bias, you will observe this negative region, and that is n-type region, and this is called as an inversion layer. That is, we are just flipping its behavior, just inverting its behavior. So that is inversion. Now how we will observe, what we will observe in this energy band diagram, you have to look into it in very focused manner. Okay, so in this is a metal, oxide and semiconductor. This is similarly, the electric field direction will be in which direction? It will be in this direction. Okay, electric field will be in this direction. So electric field will be in this direction, EOX. So electric field will always be सर उठा के जिएगी, hence upward. Electric field सर उठा के जिएगी, hence upward, upward, upward. Clear है? And here what you will observe, that here there will be electric field 0 and here will be electric field non-zero in this particular region. Okay, so what you will observe in this particular region is that, consider this region here. If we consider this x is 0 here and it is moving, increasing by the value, and here its value is x. So from x0 to xi, this particular Fermi level is below the substrate Fermi level. So in this particular region, it will behave like an n-type material. And at this, when the Fermi level of intrinsic semiconductor and the p-type semiconductor will be equal, then it will behave like an intrinsic material. And if the semiconductor, if the Fermi level of the intrinsic semiconductor is above the Fermi level of the substrate, then it will behave like a p-type material. Okay, in simple explanation, if I want to explain you, if you consider this n-type material, here I am considering this n-type and here I am considering p-type. In general, this is EC, this is EV. Okay, and if this is so in this n-type material, Fermi level of intrinsic material is below the Fermi level of the substrate, or you can say the semiconductor. Fermi level of the substrate or the semiconductor, that is above the intrinsic Fermi level, then it will behave like an n-type material. If we consider the p-type, this is conduction, this is valence, and this will be EFI and this will be EFP. That is, in p-type material, what will you will observe? That intrinsic Fermi level will be above the Fermi level of the p-type material. So this is the basic difference. Here Fermi level is of the n-type is above the intrinsic Fermi level, and in p-type Fermi level is below the p-type Fermi level. Okay, so this is only we will observe in this particular diagram. Here the Fermi level is below the Fermi level of the substrate, hence it is behaving like an n-type material. You can observe from this, you can look from this particular explanation. So this region will behave like a n-type, and this region will behave like an intrinsic, and this particular region will behave like a p-type. Clear? So this is the only thing which we have to remember in this inversion region. This is very important concept. Clear? So this is I have written in this table. You should learn that. Then in this, what you will observe that downward bending of energy band diagram will increase. As we have learned in the depletion region, there also we have seen the downward bending, but there you will observe that there will be a smaller bending. Okay, there is not much slope, but here you will observe a larger bending of the energy band diagram. Intrinsic Fermi level becomes smaller when the intrinsic Fermi level becomes smaller than the Fermi level of the p-type material. Okay, here intrinsic is smaller than the p-type material, which means that the substrate semiconductor, region become n-type. It has become n-type within this layer. So this is the inversion of that particular region. And here the electron density is larger than the majority carrier density. Here what you will observe that electron density is larger. Here electron density is larger observed. In this electron density is larger than the majority charge carrier. Here majority is holes, but the electron density is larger of the negative ions or the acceptor ions. And when we apply this gate voltage greater than the threshold voltage, then only the inversion layer will be formed. Inversion layer means inversion of its property. And what is threshold voltage? It is the amount of gate voltage which is required to create this surface inversion. Means it is a minimum amount of voltage which is required to form this particular inversion layer, that is called as threshold voltage. So is it all clear to you all? So this is all from my side. Thank you so much for watching. In my next video, I will be teaching MOSFET operation. Thank you.